So we have seen Gaussian distribution in lots of details, right? And we also understood why Gaussian distribution is important and what inferences can we make as soon as we know that something is distributed with a normal or Gaussian distribution. But we have also studied non-Gaussian distributions, right? We have studied uniform distribution, right? And we have seen that uniform distribution is useful in generating random numbers, right? It is useful in generating random numbers which are uniformly distributed. And there is a lots and lots of applications of random numbers in algorithms and even in data structures and things like that, right? In computer science in general, right? So having said that, we also learned other types of distributions like Bernoulli, binomial. We discussed some of these distributions. We also discussed more real world or distributions that occur a lot in the real world, like log normal, like Pareto distribution, etc. Right? But the universe of distributions, there are hundreds of distributions. There are hundreds of distributions in probability theory. Now you might wonder, why do we have these hundreds of distributions in the first place, right? That's so the first question is why? Why do we have these hundreds of distributions? So let me give you an example. And why do we have them, and what is the benefit of having these hundreds of distributions, right? So I'll try to explain this from the example of a distribution that we have not seen. That distribution is called Weibull distribution. Okay, I'll tell you a story behind this, right? So distributions typically, as we discussed in one of the previous videos, right? A distribution. The moment I say that, okay, a random variable follows a well-studied distribution, right? The distribution gives us a well-studied distribution. A well-studied distribution gives us a theoretical model. It gives us a theoretical model on how a random variable behaves. Suppose if you have a random variable x that belongs to, let's say, a well-studied distribution D, right? Whatever the distribution is, it could be Bernoulli, binomial, log normal, Pareto, or any one of the hundreds of distributions. And this distribution is basically a theoretical model. So the moment I know that x belongs to this distribution, there are tons of inferences that I can make about this distribution. Let me give you an example, as I was just saying. So there is this distribution called Weibull distribution. Okay. So I have a personal story with this. So my father used to work as a civil engineer, and he was responsible for designing and construction of dams, right? So he was looking at some probability tables, and I asked him, what is this, right? Of course, at this point, I understood considerable amount of probability theory. I was already in my graduate school and things like that. So he said, in civil engineering, what we do is this, right? When I have to estimate, so in civil engineering, this is, of course, he also forgot most of the theory because he's already closer to retirement at this point of time. But he gave me some very interesting lessons on how they use it in civil engineering. So he said, when we have to construct a dam, we have to understand how high this dam should be. This is a very, very important parameter. We have to understand how high this dam should be, right? How high should the dam be? Because this height is determined by how much water you want to store, right? This height determines how much water you want to store in the dam, right? Because what is a dam? A dam is basically a barrier that you draw and you let water gets collected here, right? And then you use this dam and then you channel this water. This dam literally blocks all of the water behind it. There is a flow of water in this direction. It literally blocks all of the water, and then it reroutes this water through canals, right, to the fields, or it uses this water to generate hydroelectric power, right? So the height of this dam is dependent. Of course, it tells you how much water you can store, but it also has one other angle, which is if there is more rainfall in this region, right? Because water gets collected from many upland areas, right? So the rainfall in this region, right, from where the water is flowing in to be stored in the dam. So this is the dam. This block is the dam, right? So the rainfall upstream, this is called the upstream rainfall. The upstream rainfall also determines how high the dam should be, Because if there is a lot of rainfall, there is going to be a lot of water coming into the dam very quickly, and that will determine how high your dam should be, or how many outlets you should have in the dam. Because if the dam overflows, all the villages and towns on the other side of the dam could get damaged. So to mitigate risk, to mitigate accidents, of overflow of the dam, civil engineers who are designing dams need to look into how much rainfall will occur. And remember, these dams will stay for hundreds of years, right? These dams could stay for hundreds of years with repairs. So they better understand what is the maximum rainfall, because the dam is not something that you design today that has to last only maybe 5 years or 10 years. Dams have to last for hundreds of years in some instances. They have to understand what is the maximum one day rainfall. How much is the maximum rainfall that can happen in this region? Because water gets collected from here. What is important for them is the maximum one day rainfall in the collection region or in the upstream region. Because if this rainfall is a lot, they need to have more outlets of water, and the height also should be sufficient enough that they can store all of this water, even in the worst case, so that the dam doesn't collapse and create a havoc where millions of lives could be lost. So the civil engineers had this question: how do we know? Okay, what do they want now? They want to understand the maximum one day rainfall, and they want to estimate this, right? Let's assume this is your random variable x. Okay, now they want it to estimate what is the probability that x is greater than or equal to, let's say, 20 centimeters of rainfall. Okay, this is very, very important for them, right? If you think about it. Of course, what they would have here is they would have rainfall data, right? They would have rainfall data for, let's say, last 30 years or so, or maybe 50 years of data, right? So they may have a few hundreds of points. They may have few hundreds of data points, right? Because this data would be collected only on those days where there is a rain, right? So the data that they're collecting is what is the maximum one day rainfall that they had in a season, or they had in a week, or something like that, right? They need to understand this probability, right? Because if they understand this probability, they can design the height of the dam and the number of outlets in the dam for the water to go away. And they should be extremely confident. They should be able to say that if the probability of the maximum rainfall to be greater than 20 centimeters is, if this probability is very, very small, let's say this probability is less than or equal to 0.1%. This means it would happen 1 in every 1,000 cases, right? Or if this probability is significantly less, maybe less than 0.01%, they want to measure these probabilities, because this would help them understand what is the maximum possible rainfall that would happen in this region, which will help them determine what the height of the dam should be, right? This is a very real world problem. Now, how does a civil engineer solve this? Okay, a civil engineer will now have a few hundreds of data points. Remember, all of this was done before modern computer science, before modern computers. Okay, modern computers were only available in the last 50, 60 years to even civil engineers, right? So even before computers existed, how did civil engineers design the height of the dams? So they would collect a lot of data. They would collect few hundreds of data points on how much is the maximum rainfall in a season or in a week, right? Maximum one day rainfall. They would collect all of the data. Let's assume they get some data here. Okay, so they got some data here. Okay, so in one week they got 10 centimeters. The other week they got 5 centimeters. In the rainy season they got probably 15 centimeters. Other week they got 16 centimeters. So on and so forth. So let's assume they have few hundreds of observations, right? They have few hundreds of observations. Now the biggest question is, okay, they want to estimate probability, and these are all observations of x. They want to estimate what is the probability that x is greater than or equal to 20 centimeters, right? This is the question that they have. Now let's be more specific, right? Now to estimate this, there are two ways. Okay, one is I take percentiles. I will say Where does the 20 centimeters lie here? Or I can use distributions. Okay, let's see how to do both. So let's assume, to be very specific, let's assume I have 200 observations here. Let's assume I have only 200 observations here. Okay, now I'll ask the question, what is the probability that x is greater than or equal to 20 centimeters in these 200 observations? Okay, let's assume only 4 out of these 200 values, or let's say 1 out of these 200 values is greater than or equal to 20 centimeters. Then using the percentile method, I can say that the probability that x is greater than or equal to 20 centimeters is 1 by 200, right? Which is roughly 0.5%. Okay, sorry, which is roughly 0.5%, which is roughly 0.5%. But here we are using the percentiles, and I have only one observation here which is greater than 20 centimeters in my whole data. Here, remember, before modern internet and computers, right? Collecting few hundred data points is very, very expensive. In the internet world, right? In the world of Google search, Amazon purchases, Facebook, obtaining millions of data points is very, very easy. Obtaining millions of data points is very, very easy. But in the pre-computer era, collecting even few hundreds of data points was very, very time taking, right? So we have to put ourselves in the shoes of a civil engineer who is designing this system, let's say 1960s or 1950s, let's say. Okay, where computers was not widely available. Only a few research labs in the world had computers. But he had this data. Let's assume the meteorological department of that area was collecting the number of the rainfall data in that region. Without rainfall data, you can't do anything anyway. Okay, but let's assume we have only 200 observations. From these 200 observations, I have only one observation there which is greater than 20 centimeters. So this probability that is estimated is going to be very bad, is not going to be trustworthy. It is not trustworthy. Because I have only one observation. If I use the percentile way of solving the problem, right? If I just see, okay, how many of these points are greater than 20 centimeters? If only one of them is greater, this one is like, I can't trust this 0.5%. So in the world where observational data was scarce, was not readily available in millions of data points, people said, can I build a theoretical model? So the civil engineer here would take your 200 observations, your vector of 200 observations, 1, 2, so on, 200 observations, right? Which is literally this data. The civil engineer now, because this is not, I can't trust this number because there is only one observation. If there are no observations, what do I do? Would I say that the probability of that is 0%? It's not, right? So what people did was people tried to fit a theoretical model. Given this data, people said, can I fit a known and well-studied distribution? Can I fit a well-known and a well-studied distribution or theoretical model? What is a distribution? It's not a well-studied distribution or nothing but a theoretical model. Or can I build a theoretical model to this data? Then, right? And there are hundreds of distributions, right? There are hundreds of distributions. So people who are researching this area, not the civil engineer, but probably people who are teaching civil engineering, or university professors, or expert designers, or expert, like really, really expert, people have done this long back, by the way. They would say, of these, they would try with hundreds of this distribution. They would first try Gaussian distribution. Okay, they'll see if these 200 points fit the Gaussian distribution. The answer is no. Then they'll try log normal. Okay, then they'll say no, it's not fitting the log normal distribution. And how do they do these tests? There are two ways of doing it. You can either use the QQ plot for a visual approach, or there are tests like KS test that we will discuss later in this chapter, right? So there are multiple tests for each of them. They try all of this distribution. Let's say one distribution called the Weibull distribution fits the data fairly well. Let's just say that Weibull distribution fits the data well. Now your question is, again, Weibull is a well-studied distribution in particle physics. This was actually discovered. This Weibull distribution was created by particle physicists. So let's go to the Wikipedia page here. Again, I'm on the Wikipedia page for Weibull distribution, right? Here it says that one of the applications in hydrology, look at this. This is one of the applications in hydrology. Weibull distribution is used to measure the annual maximum one-day rainfall and river discharges. This is used in hydrology and dam construction. Okay, but there are many places where Weibull distribution occurs. It occurs in electrical engineering, in industrial engineering, weather forecasting, information retrieval, insurance. There are many places where it occurs. But if you go to the top of this page, you'll see the history of it. So Weibull distribution was created by Swedish mathematician Valery Weibull in 1951, although it was first identified in 1927 and 1933 to study particle size distributions by particle physicists. So Weibull distribution was created to understand particle sizes in physics. But the same distribution happens to also fit this data of maximum rainfalls. Now the moment, see, this is the moment I know that it fits Weibull distribution, now I know that my random variable x, which is maximum daily rainfall, right? The moment I know this follows Weibull distribution. Of course, Weibull distribution will have some parameters. Now I estimate the parameters. Remember how we estimated mu and sigma in the case of Gaussian distribution. Similarly, Weibull also will have some. So if you go here, it will tell you what are the okay. Weibull has two parameters, right? Lambda and k, and you can determine lambda and k. There will be some formula to determine that, right? Based on your mean, median, etc. Let's assume we have the parameters also of Weibull distribution. Now Weibull distribution is very well studied. The moment I know x is Weibull distributed, I know all the properties of Weibull distribution. I know its PDF, I know its CDF, I know all of it. So the first step is, okay, let me write it down. The first step is that I determine that x belongs to Weibull distribution. The second step is I estimate the parameters of the distribution. Now when I do that, I can obtain the CDF and PDF. Once I have the CDF and PDF, now determining the probability that x is greater than or equal to 20 centimeters is nothing but 1 minus probability that x is less than 20 centimeters. And this value I can get directly from the CDF of x. I can simply get it from the CDF of x. Now, the fact, see, when I try to use a non-parametric method, or where I'm not estimating any distributions, a non-parametric method is like using medians, percentiles, quantiles, etc. Where I'm not making any assumptions of distributions. There, I got a percentage of 0.5, but I can't trust this because I had only one observation. But now, what have I done? I've taken the data, I've tried all the distributions, and I figured out that Weibull fits the data very well. Now, the moment I realize that Weibull fits the data, right, I can find this, and whatever value I get from this is more trustworthy. Now your question is, why is it more trustworthy? The answer to that is because 200 values fit Weibull distribution, while in the other case only one value was greater than 20 centimeters, right? So instead of deciding what this probability value is based on just one observation, it is better to use all the 200 observations, fit a distribution, and we know people have studied this distribution very well in other areas of science. So I'm using all the 200 values here to fit a distribution, and using these 200 values and the distribution and the parameters of the distribution, I'm estimating this data, and hence this is far more trustworthy because I'm using all the 200 values and not just the one value that I have, like in using the percentiles. Right? And this is what a lot of physicists, engineers, scientists have done for many years. So when you have a distribution, right, when you have some data, I hope this rainfall data gave an appreciation of how these distributions were used in the pre-computing era. And it's very important because the moment you know that something belongs to a distribution, and the parameters of the distribution, you have the PDF and CDF, and you can answer tons of questions about it. Right? Now, so all the distributions that we studied occur a lot of places. And remember, this Weibull distribution was studied by particle physicists, but it's now used by hydrologists and civil engineers who design dams. Right? So very interesting part of. So now it's a very interesting idea, right? That Weibull distribution that was discovered by particle physicists to measure particle sizes, right, is also used now by civil engineers and hydrologists who design dams. Of course, my father didn't know many of these details. He was just following a chart table that civil engineers have been using for almost generations. Okay. Of course, he probably studied this in his college and has forgotten some of this because his college was like some 40 years ago. But this is the logic behind it. So this helped me understand the value of distributions to non-machine learning people. The reason I'm giving a non-machine learning example here is so that you appreciate that these distributions are not limited just to machine learning. They're applied in almost all areas of science. Right? Now we also studied Box-Cox transform, right? We also studied Box-Cox transform a while ago. Now imagine I have some data. Okay, belonging to some distribution, most likely a Pareto distribution or a log normal distribution or log gamma distribution, one of these distributions. Box-Cox distribution transforms your random variable to a new random variable. Not always, sometimes your Box-Cox transform can help you transform your random variable, which could belong to non-Gaussian distributions. Okay, this is a non-Gaussian distribution. It can transform it to a Gaussian distribution. Right? Using whatever your Box-Cox transform, it's also called as power transform, right? Now, the moment I have my x dash, which belongs to Gaussian distribution, I can perform all of my analysis on this. I can perform all of my analysis and answer questions based on this. So let's assume, hypothetically, let's assume that my x, okay, which is these 200 values of rainfall, let's say, okay. So let's assume I don't know about Weibull distribution, or Weibull distribution was not discovered. Okay, let's assume this is my max daily rainfall, max 1 day rainfall or daily rainfall, right? Suppose I pass it through Box-Cox transform, and Box-Cox transform, let's assume, creates a new random variable called x dash, which is Gaussian distributed. Now I can transfer all of the 200 values that I have here, right? I have the 200 values for x. I can pass each of these values through the Box-Cox transform and get values for x dash, right? So this is, let's say, x1, x2, so on and so forth. This is maybe x1 dash, x2 dash, x3 dash. Because Box-Cox transform is basically a simple exponentiation or a log operation, right? I can apply it on all this data also. Now, if I know that x dash is Gaussian distributed, I can perform all my analysis on this, right? So probability of x greater than or equal to 20 centimeters would be equivalent to probability of x dash greater than or equal to some other value. Okay, let's call this value delta, because I need to transform the 20 centimeters through the Box-Cox transform and get my delta. Right? This probability will be equivalent to this probability, because Box-Cox transform helped me transform the data from x to x dash. And I know the moment I know x dash is Gaussian distributed, I can easily estimate this from the CDF of the Gaussian distribution. Right? So Box-Cox transform is also helpful because it can transform data which is non-Gaussian distributed to Gaussian distributed. Again, not always, but sometimes. But the moment you make that transition, you can use all of the data, all of the knowledge, all of the well-studied properties of Gaussian distribution to answer these important questions about data. Right? I hope some of these concepts are clearer now. The reason I'm taking this much time to explain the specific applications of non-Gaussian distributions is they occur a lot of places. They occur in lots and lots of places. You'll be surprised in how many places we see non-Gaussian distributions, right? We see log normal, we see Pareto, so for example, let's go to the log normal distribution page, right? So if you go to the applications of log normal distributions, right? Occurrence and applications, there are tons and tons of applications of log normal distribution in human behaviors, in biology and medicine, in chemistry, in hydrology, right? In social sciences, like in economics, finance, city sizes, in technology, wireless communications, you name it, right? So some of these distributions occur in lots of places, even though they were discovered, right, at some other place. They occur so many times that they're well enough to be studied. So there are hundreds of such distributions that mathematicians and statisticians and practitioners and engineers and scientists discovered over a period of time. And what they help us achieve is, very, very importantly, they help us give a theoretical model. The distributions help us give a theoretical model on how the data is distributed, right? Because we could have answered this even using percentiles, but that's not good enough because we're using only one data point here. While the moment I fit a distribution, I can use all of the data to fit the distribution and understand the properties using the theoretical model.